Thanks everyone for being there. My name is Florian. I'm working at Google as a software engineer on the Android games team. And there is two things that I like in life. It's making applications and video games. That's why I created gdevelop. It's an open source cross-platform game creator that people can use to create any kind of 2D games. And it's a visual editor for games, so there is a level editor that I will show just after. And there is some kind of visual programming so that anyone can create games, the rules of the game, without having to really do any kind of coding. And at the end, you're getting some HTML5 games that can be outputted and played in a web browser or even on Android, iOS, or on desktop. So that's what the software used to look like. I say used to because that's the old version. So it was all written in C++ as a desktop application that you could download for Windows, macOS, Linux. So I will quickly show you how it was working and the visual programming I was talking about. So you can see that there is the level editor on the left, so it's done using OpenGL, and you can create the level of the game. And on the right, there is a list of objects that are in your game. So, for example, you have the player, the platforms, the button that is in the middle of the screen, and so on. And what I want to do is to add some rules to the game so that when the player is stepping on the button, then the platform that is on the right is going a bit up in the air so that the player can step on it and continue in the level. So let's see how to do it. So I'm putting the button on the level, and now I'm adding these visual events. So events are composed of conditions and actions. Here I'm adding a condition to tell that if there is a collision between the player and the button, then in this case I will launch two actions. It's a if-then. So the first action will be to change the animation of the button so that it goes in the state where it's pressed. And then I'm adding another action, which is one to move, yes, to add a force, to add so that the platform is moving up in the air. So on the y-axis, I'm adding a force, and now I can press play, and the whole game is compiled to JavaScript, and it's run in a browser. And when I'm stepping on the button, yeah, it's working. So see, it's fairly simple. It's programming, but for people that don't want or don't have the time to learn a new programming language. And it's working fairly well. People have been creating lots of different games with this. I've done the one with the cat on the top left. Yeah, things were going all right, but at some point, the whole editor was getting quite old. I had lots of cross-platform issues with the UI toolkit, and especially on macOS and Linux, things were crashing from time to time. And iterating of the software was quite slow, C++. Building the UI was slow, and I was limited to old UI components, the native one. And honestly, the UX will need quite a lot of enhancements. And also, the entry barrier for new contributor was quite high, C++ again. So yeah, it was time for me to react. And my question was, could the web technologies help? Because I've been using quite a lot of React before in my previous job, and I was like, I feel that's a better way to do things. I think that it's perfect for making complex UI. Or is it really? Can we have, for example, a list of trees and of hundreds of elements, dynamic panels, 3D visualization, nested dialogues, drag and drop search, and everything that make your app looks like a real desktop application rather than a web app? Can we make ambitious applications? Same with JavaScript. It's perfect for most applications, or is it really? What if we have an already existing native code base, like I do, or if we want to do advanced computation, or if we need consistent performance? Well, let's take a look. This is the whole C++ code base of the software. Well, that was the code base. So there was, in the middle of the code base, the core classes, what a game is, what an object is, what a texture is, and the game exporter. So that's taking this model of a game and transpiling it to JavaScript as a WebGL game. And on top of it, there was everything related to the graphic interface and the file system. So I was thinking, OK, I could redo the whole interface using React. And for the file system, I could change it to use Node.js and also browser adapters and run the whole thing on Node.js or Chrome, or run it or package it using Electron so that I have an application that people can download. And what to do with the C++ code base? Well, I could compile it to WebAssembly. let's see this part. So if you don't know about WebAssembly, it's a low-level language that is running in your browser, in all evergreen browser. It's supported even on mobile phones, on Android and iOS. And it's a low-level language, meaning that you're not writing WebAssembly, but you're compiling from another language to WebAssembly. And it's running fast. It's running fast because as it's assembly-like, browser can optimize it much more quickly than JavaScript, and you get consistent performance. So I said that we are not writing directly to WebAssembly, but using things like, for example, Emscripten, which is a project to compile from C++ to WebAssembly, or using a language like Rust or other languages that are compiling to WebAssembly, or you can even try it using assembly script, which is a language that looks like TypeScript and that compiles to WebAssembly. In my case, I've been using Emscripten because I had this C++ code base that I wanted to port on the web. So I will describe how it works, and then we'll see the part about remaking the whole interface in React. So first, first Emscripten. If you want to try it, it's not that complicated. You have to clone the SDK with these commands that I won't detail, and then you're getting a compiler called emcc that you can run on a C or C++ file, and you're getting, as the output, a JS file that is running a WebAssembly file. For larger projects, Emscripten is providing you with a replacement for your compiler so that you can swap your project build, and instead of getting a binary, you will be getting a WebAssembly module. So in my case, I'm using CMake, but depends on what code base you're trying to port to the web. So if you're compiling the whole thing to WebAssembly, you have this huge chunk of C++ compiled to WebAssembly, and that's not enough. You have to expose the existing classes in C++ or Rust or whatever your language so that you can use them in JavaScript. Let's take an example. Here is a layout. It's a scene. It's a level of a game. It's a C++ class, and you can set the name, get the name of the scene, and you can insert or get an object on the scene. Though that's just an example. We don't really care about what's inside this code. The idea is that you have to write the interface so that Emscripten can know what classes to expose to JavaScript. So that looks like this. There are multiple ways of doing it. In my case, I've been using something called WebIDL. It's an interface definition language. It's used by the W3C to write the specification for the DOM. It's also we can also use it to show to Emscripten what should be exposed to JavaScript. So here, I'm rewriting the interface of the class, the layout, with two methods, setName, getName, and two other methods to insert and get an object. You can see that the types are slightly different, and the idea is that you have to look at the documentation of Emscripten or your language to see what type are being converted in your language and to JavaScript. Once you have it, you can run it, and Emscripten will be compiling your C++ code to WebAssembly, and including these bindings that you've been writing, generating some kind of glue code that is calling from, so that when you call the JavaScript class, it's calling WebAssembly. That looks like this at the end. You have a module that you instantiate, getting the object in a promise, and then you can create a new object, here, layout, call a function on it, like setName, same with other objects, and you can even console log the result of a method returning a string, and that's working well. The primitive types, like numbers, booleans, are automatically converted to their equivalent in your host language. So again, look at the documentation to see, for example, the JavaScript strings are converted to an array of characters in C. If you pass an object, you will get a reference to an object or a pointer in C++. And if you want to output things in the console in C++, it will be automatically redirected to the console in your debugger. So that's what you're getting if you're running the whole library in the Chrome debugger. So you can see that on the top there are some logs that are outputted by the C++ library, so it's working. And then you can create an object and call a method and get the result of another one. So yeah, you're having something working in your browser, even if it's written in C++ or Rust or something else. So that's a pretty good first step. There are a few things to know. First, the memory management, it requires care. Because if you're creating something in the WebAssembly world, you have to destroy it. Meaning that, let me explain. If you're creating a layout, which is an object created in my library, if you console.log it, you see that it's not a real JavaScript object. It's a JavaScript object containing a pointer to some number, which is a number that is pointing to some part of the WebAssembly memory. You can think of the WebAssembly memory as a big array that is empty at the beginning. And when you're creating a new object, the WebAssembly code is running some constructor to create your object in memory. And so it's an array of bits, basically. If you don't destroy it, if you just forget about this layout variable in your JavaScript, then the reference to this memory is lost forever. Basically, you have a memory leak. So you have to remember to call the GD, well, the module.destroy method that will be basically running the destructor in C++, Rust, whatever, and will release the memory. So that's something that you have to remember to do. And for example, if you're using a React, that means that when you're mounting a component, if you're creating an object in the WebAssembly world, be sure to destroy it when the component is unmounted. Or you can use an effect hook. The second thing to know is that the output of the WebAssembly module will be quite large. It's 3 megabytes for gdevelop. You can compress it, and it's only a few megabytes. Honestly, I don't really care because I'm making an application that is a rich application, so a few megabytes more or less, that's the same. I'm not happy, but I'm fine with user having to wait a bit during the loading time of the application to get this because it's a rich experience. And also, the whole thing can be downloaded using Electron, which is a few 100 megabytes, so one more, one less, same thing. Some last thing to know is that you better have a complete test set for your library that is compiled to WebAssembly, because this is the kind of error that you're getting if something is going wrong in your WebAssembly module. So it's not useful at all. And that can happen if, for example, you pass a wrong type of parameter to a method or you forget a parameter. In this case, your WebAssembly code will be expecting, for example, a pointer to an object. If you pass instead a number which is meaning nothing, then it will go to some place in the memory where there is garbage and bad things will happen. That can also be the case if you're using a deleted object. So these things are a bit manual work that we are not used to do in JavaScript, but once you get used to it, it's fine. And it's mainly to remember to always use an object after creating it and deleting it, and to make sure to pass the proper types for the parameters. This being said, we now have the core of the application that is compiled to WebAssembly and running in a browser. That's a good first step. Let's now see if we can redo an interface on top of it that is better than what we had before. So we want to make a complex UI, and by complex UI, I mean a UI with context menu, thumbnails, list of objects, trees, dialogues. So the first thing I wanted to do was to find a component library. Material UI, React Toolbox, Blueprint, whatever. My idea was to find something with an extensive list of high-quality components, good theming support, accessibility, maybe the most important thing, and a good documentation quality. In my case, I've been using Material UI, but others can be fine too. Then the first change I had when remaking this whole interface in React was to display large list of objects. And when I say large, it's sometimes hundreds of elements or thousands. For example, the list of objects in a game. In this case, using virtualized list has been really useful, using, for example, React Virtualized or React Window. And the idea is that instead of just mapping on a list of objects and displaying all of them in the DOM in the browser, the virtualization library will give you a list component with a function here called row renderer, and this function will be called to render only a subset of the list, which is the objects that are to display on the screen. So if your screen is displaying 20 objects, you will only have in the DOM 20 objects rather than 1,000. And then when you're scrolling, some objects are being removed from the DOM and others added. You can even use React D&D if you want to add drag and drop to the virtualized list, and it's working fairly well. The next challenge that I had was to display some panels or resizable editor, because as I'm making a game engine, a game editor, people want to be able to customize their workspace. And it's not something that we really used to do on the web, but turns out that there are libraries that are doing this for us. So basically, take a look at React Mosaic. It's awesome because it's giving you a kind of window management library that is doing everything for you, and so you can have a workspace that a user can customize. So it's really great. Then the next challenge was to display large trees on the screen. So you can see that's the event editor that was done on the left in C++. In the native application, it was quite complex and honestly hard to maintain. It was a 2,000 line of C++. So here I've been using, again, another library to make this tree of events, because events can have sub-events. It's a bit like a code blocks that can have well, not sub-events, but other code blocks nested inside. Anyway, here, virtualization, again, is really useful. I've been using a React sortable tree, which is giving you a good start if you want to make some kind of business rules that you can drag and drop on the screen. In my case, I'm using a heavily customized version of it. And I think maybe the most complex thing to do was to remake the whole level editor that was done before in OpenGL, and now that I wanted to have on the web. At this point, using the DOM was not an option anymore. You can forget about it and start to think about using WebGL. Well, using WebGL, it's a bit harder to get started, so I've been using a library which is called pixie.js. Which is it's a rendering library, rendering on WebGL or Canvas. And there is also Phaser 3.js. Anyway, think about it if you have to do something that is a bit too complex for the DOM, like 2D rendering of some of thousands of elements, like a level in a game. Still, sometimes the DOM can be useful. Let's say that you want to have an editor where you're displaying the polygon, the hitbox, the collision mask of an object. So in my case, I want people to be able, in their game, to say that this red area is the place where the spaceship of the player can be hit, and the rest is fine. In this case, the DOM using SVG element can be really useful, and especially consider that you can use the on pointer move up and down events. You can get a polygon that you can display on screen quite easily using React or your favorite front-end framework. And yeah, using this on-pointer move up and down events, you can get something that can be dragged and drop on the screen, so that I can go on the vertex and then drag it. So you have a visual editor for a polygon, and it's done pretty easily. Sometimes things are not fast enough, meaning that things are too slow to render on the screen. In this case, the best bet is, in the case of React, to use the React profiler. So for example, if you have something that is too slow to render, take a look at the profiler. It's displaying in all the components in your application, and it's coloring the components that are being re-rendered after an interaction. And so in my case, you can see that the left part is filled with lots of colors, and it's because some panel that was not even displayed on the screen was being re-rendered after each interaction, so that I was getting lots of, I was getting a performance hit for something that was not even on the screen. So in this case, the profiler is really useful, at least to sanity check that you're not re-rendering more than needed. Something to remember, measure performance of your application in production. At least in the case of React, I'm less familiar with other front-end frameworks, but in the case of React, the development build is way slower because of the warnings. So it can make a difference. Something that is taking like 1 second in development can be a few milliseconds or less in production. And sometimes things are slow because you're not slow during the rendering, but you're calling too much of WebAssembly methods. So beware of the overhead. When you're calling WebAssembly, the JavaScript has to convert your parameters to some kind of representation in your host language, meaning that if you're, for example, in this case, if you're filtering and mapping on a list of 100 or 1,000 of objects, and for each of these objects that are WebAssembly objects, you're calling a method, like, for example, here, getType or getVariables, that is giving you back a string. All of these things have to incur a cost of converting from a WebAssembly string, well, a C++ string, to a JavaScript string, and that can take a bit of time. In most cases, it won't be noticeable, but still might be a good idea to store things like the strings or the value on the JS side, so that you don't have to cross the gap between JavaScript and the WebAssembly world every time you're rendering a component. Sometimes, at some point, your code base is growing. In my case, as it's an open source software, I'm getting contributors. And here are a few tips to keep your code base sane. The first thing is to just have components for everything. If you have an help button, if you want to have this help button that is a bit smaller on the screen, don't just add the font size 12 and be done. Just create a new component for it. What I'm saying basically is have a design system and stick to it. I'm not unit testing my visual components, sorry. Well, actually, I do, but only if there are some part where there is logic. What I do is to create visual stories. So using Storybook or React Style Guidist, you can create stories that are your components working outside of your application, so that you can work on them and test them without running the whole application. It's very useful when, for example, you want to test that your component is displaying some kind of errors that you're not seeing in real because your software is working properly. That's a huge advantage of a native development because you don't have to relaunch your whole application every time you're making some small changes. Finally, make sure to use types. Either Flow or TypeScript, I don't care. Just types will tell you that you forget to pass a prop or to remove a prop. It helps for auto-completion. It avoids most silly mistake, or not so silly sometimes. It helps to document the objects. So I think that types are really shining when you or someone else is refactoring some part of the app. And remember that after a few months, you will be a stranger to your own code base. This being said, I think that we have now the core of the software that is transpiled to WebAssembly. We have a new interface done using React.js. Just a few words about packaging the whole thing. You can either package this as a progressive web app using Electron, or even embed the whole thing in a native application. Whatever you choose, my advice is to build over the existing APIs. For example, in Electron, you have APIs to make context menus. Better use them to get a native feeling if you're distributing your application as a downloadable application. So yeah, that seems to work. Let's see the result. So this is the new application running in Electron, but that can run in a web browser too. And I'm doing the same thing as before, meaning that I'm creating a button object, and I will put it on the screen, and as before, adding a few visual events so that when I'm stepping on the button, then the platform is going up in the air. So yeah, I'm putting the button on the screen, and same thing as before, I'm adding a new event with a condition so that if there is a collision between the player and the button, then the platform will move. So you can see that it's more or less the same thing. It's a bit old actually, so the interface has been changing a bit again, but you can see that it's a bit the same thing internally. Yeah, I can press play, the whole, oh no, sorry, I forgot the second action to change the state of the button. So yeah, when I'm done, I can press play, and the WebAssembly module will be compiling the whole thing to JavaScript, and you have a game running. And yeah, that's working well. Or at least, for my definition of a developer, it's working well. What are the users saying? Well, I'll be honest, the first feedback about the application were really bad. Why? Because people were used, it was not because it was done using Electron or React, or it was some kind of web application. It's just because even if the core of the software was the same as the previous version, the whole interface was new, and so I was missing features. And so people were complaining about this lack of features. And after a few months of work, adding new features back like the previous version, people started to say, oh, okay, that is better. That is better than the old version. I can even be more productive on many aspects compared to the old version. And now people are almost entirely using this new version compared to the old one. So it works. It works so well that the native app is better. The native web application is better than the entirely native application. Why better? Because I can iterate on it really fastly, because rather than waiting for 1 minute for the C++ code to compile whenever I'm making a change to the interface, I have to wait only 10 seconds for Webpack to compile the whole things, and 10 seconds is too much. No, it's not that much compared to before, and I can test it really fast using Storybook. I have a near-perfect cross-platform, almost no issue, no crash. I can develop on macOS and distribute it to Windows, and without even testing. I'm still doing some tests. I have a faster startup time, auto-updates, more contributors. I can try it online. I think that's something that was not even possible before. You can go online and try the software without even downloading it. I can port it to a phone, and yeah, it's actually working on a phone. It's not made for, but I'm adapting the interface so that it can run fairly well on a recent phone. So I think that's it. I wanted to show with this talk that with web technologies, we can be ambitious and make things that are as good, if not better, than what we used to do in the native world. Thank you.